Good morning, everyone. Good morning. So thanks for joining us on the third day. We know, Geo for Good, there's a lot of energy that you need to bring every morning, so I hope you've got your coffee and your breakfast. Whether you're here in person, whether you're attending virtually, it's really wonderful to be together again. I've really appreciated the power of this community over the past 10 years or so that we've had, 11 years actually, that we've had Geo for Good. But I didn't appreciate it as quite so much during the pandemic. I think my appreciation has just grown for all of you, and I'm really excited to be here in person. So thank you for joining us, for making the effort, traveling all over the world, and coming, or joining us on screen, joining us virtually, and making the effort to be here today. So I want to welcome my partners in development of Dynamic World at the World Resources Institute, represented by Fred Stolle. As well as a very special guest speaker, Jason Schatz, who's the CTO at SkyTruth. And they've been using Dynamic World for land use change change detection in a really interesting way. So humans have drastically changed the surface of the earth. We've cleared forests, wilderness for crops and cattle. We've built roads and houses, and we've made innumerable land use decisions on how to use our land. We're pretty good at expanding our own habitat as a species and extending our own species range maps. But now our planet's at 1.2 degrees Celsius warmer than it was at the dawn of the Industrial Revolution. And without immediate course correction, we're getting closer to surpassing the 1.5 degrees in the next 5 years. So we have to halt the destruction of nature. And each year, destructive land use practices are responsible for 12 gigatons in net emissions, or 25% in total emissions. So we need that source of carbon to become a sink. And now I hand it over to Fred to tell us a little bit more about it.
Thank you, Tanya. I'll tell a little bit more on the driving forces. You saw all those changes that's happening, as Tanya just showed us, and the impact on climate change that has. Nothing in life is certain, but change is going to happen. And change on land cover is happening faster and a bigger extent than ever before. And those drivers, as you see, I name a few here on this slide. We need to produce more food. We need to produce more feed for cattle. We need to have more fiber for our construction. And so a lot of extra need to produce for our growing planet. On the other hand, we want more land for forests to restore and for forests to protect. So we got a lot of drivers of change in the land. Over the last 20 years, we had around 800 million hectares of change. And 800 million hectares is roughly the size of continental US. So in 20 years, that amount changed. And it is speeding up. And then to think about, we only have 13 billion hectares to play with. That's the Earth. That's the one Earth we live on. And that's where we have to get all our productions, all our protection, and all our restoration going. So that land needs to be taken care of. We don't want to overstretch and get in a situation where we actually get overproduction, get our production so far that it actually collapses. So land is fundamental in our thinking, and land cover is basically the global Earth's base map for so many other things. If you think about the importance of climate, Tanya just said it, but also if you just leave vegetation alone, it stores so much carbon. Only way you disturb it, it's a big source. And so we need to get it more as a sink. Of course, it's important for biodiversity. I don't have to explain you that. We are still 3 years in the zoonotic, epidemic, the interface between nature and human, highly important, all related to those land covers. So land cover is very basic, although I think it doesn't get the attention that it actually needs to. To make a little bit of a sidestep here, my organization, the World Resource Institute, started almost 10 years ago with Google on Global Forest Watch, where we thought we need to better understand how forests are changing. Now, in this next phase, we actually have a new initiative, Land and Carbon Lab. And again, we're very happy to do it together with Google to actually think about what about all the other land uses we need to think about, because we need to produce, need to protect, we need to restore. So how to go about it? We thought first, let's think about the 9 main building blocks of land cover. Nothing, nothing exciting, everything you understand, agriculture, forests, water. So can we follow that through time? And you can imagine if you have 2 years, 9 classes, you get more than 80 classes of change. You go over 10 years, there's a lot of change to think about. So can we follow that through time, those 9 classes? The other issue we had, because these are the 9 big building blocks, but in a certain area, it might be incredibly important to actually look at agroforest or to open woodlands. So can we actually construct a system that can look at these large changes, these large building blocks for national interest, for global interest, but also can we make it a system that actually can look at specific changes for an area where agroforest is important. And so that was the task we set ourselves. And how we got that task going, I gave it back to Tanya.
So there's a good cliche that you can only manage what you can measure, and with increasingly available and advanced Earth observation technology, we can make these wiser decisions about land use. And we're getting these massive amounts of data from satellites in near real time. So why can't our ability to monitor the planet also be able to keep pace with the Earth's rate of change over time? So the real world is dynamic, it's not static. The surface of the Earth changes with the people and the processes that shape it. And many of you have already heard about or been using Dynamic World, this new data set. It's global, 10-meter resolution data set detecting 9 classes of land use, land cover, continuously updating everywhere around the world. And it can show us how every part of our planet is being used, whether it's forests in the Amazon, agriculture in Asia, urban development in Europe, or water usage in North America. And we made every aspect of what went into producing Dynamic World freely and openly available. That's the model with an open license, the training data, the test data, the validation data, and a description about how we produce Dynamic World. And that just came out in June in a Nature Scientific Data descriptor paper. So our community is served by this open and freely accessible Landsat and European Space Agency Sentinel imagery collections. And we leverage this in Dynamic World, and a lot of you here leverage these open data sets. It's Sentinel-2A launched in 2015, and Sentinel-2B in 2017, 10-meter spatial resolution, 5 days revisit time, 12 terabytes of data per day. And again, this open and free and full data policy. We also used the entire 12 bands of TOA as opposed to surface reflectance. So what we're looking at here is how we created Dynamic World. So we used a large human-labeled training data set produced by National Geographic Society, and we teach computers what's observable in the satellite imagery. Where are the trees, where's the water, where's the grass, and so on. And then you show the model an image that it's never seen before, and it makes a prediction on the land cover class. And then from there, we run the model over 10 million scenes of satellite imagery using AI platform and Google Earth Engine. And as new Sentinel-2 scenes are available, we use the ones that are less than 35% cloudy and run them through the model to produce a new Dynamic World image. So this data set's available from mid-2015 to roughly 2 to 5 days. There's a slight lag between when we ingest the imagery and when we run the model, but it pretty much keeps pace with the Sentinel-2 L1C collection. And we plan on producing Dynamic World into the future. So it's one of the largest computed land cover data sets produced to date. And the Earth Engine public data catalog's about 70 petabytes. So do we have any kind of guesses, ballpark, what the Dynamic World collection would be? Raise your hand or shout it out. 3 petabytes.
Do we hear more? More than 3?
Eddie. It's over 10 petabytes in size. It's still growing, right? It's a seventh of the entire data catalog. It's been run over 10 million scenes, Sentinel-2 scenes and counting. And it's roughly 5,000 new images every day are added to the Dynamic World collection. And we still get really excited about big data, even though it's a little 2015. And before I hand it over to Fred to show some early insights from the data, I really want to emphasize, if you walk away, it's day 3, it's been a lot of stuff to remember. If there's nothing else you remember from this talk, remember these 2 things. Dynamic World produces class probabilities across 9 land cover types for every Sentinel-2 scene less than 35% cloudy. And that's number 1. Number 2 is, it's not a static map. It's most useful as an input for researchers, you all, to produce these custom derived maps using local knowledge and locally relevant data. So, we see a lot of the power in, off the shelf without having to be a GIS analyst. You can pick a time span, you can reduce the collection to suit your needs. It's not a top-down land cover data set. So in response to what we heard people asking for, they want to create their own regional data products, right? They don't want this, we sort of came up with this informal slogan, map with you, not for you. And because really at its heart, Dynamic World is a tool to help you build your own custom maps. And yeah, so we've got this sort of map with you, not for you slogan to sort of inspire what the Dynamic World data set really is. And let's dive in a little bit more to the probabilities. So what do I mean by per pixel probabilities across 9 classes? So if you take this single scene prediction in Hungary, that's 1 Sentinel-2 tile that's in the Dynamic World image collection. And if you focus on the region in the center, Dynamic World predicts a mix of crops and trees. And let's take a look on the ground. So visually, this looks like a relatively strong crop signal, right? So let's go 1 level deeper, and we can visualize these predictions at a pixel level, or visualize at a scene level. So now we're looking at all of the, the crop signal at a per scene basis, isolating these class probabilities, and which we've done now here for crops, and then also for trees. And this visualization helps us understand the richness and the depth of the data. I have another example from the master of visualizations, Valerie Pasquarella. The Golden Gate, this is a San Francisco Bay Area. We're looking at sort of the Golden Gate Bridge. Here's satellite imagery base map from Google Maps and Earth. And here is the top 1 highest probability class. And what if we use, this is what she asked herself, what if we use these class 1 probabilities, or sorry, the entire Dynamic World class probabilities, which all sum to 1 as weights to create a blended palette. And this is what we see. So in the top 1 prediction, there's no hint of any bridge at all. And if you look at this blended palette, you can see this finer scale spatial structure not observed in the composite of the top 1 labels. And you start to see the bridge. The other visualization that is the default way to view Dynamic World is this hillshade. Is this hillshade, which essentially you can start to visualize this distribution and the probability of the water class in the bridge region using this hillshade visualization, which predicts, if you click on the pixel over by the bridge, it predicts a mixture of bare ground and water for that 10 meter by 10 meter S2 prediction, a single scene prediction. So now I'm going to hand it back to Fred to share some early insights from Dynamic World.
Thanks, Tanya. And so just to think about this, like what I said at the beginning, they have these 9 boring building blocks, but with these probabilities, we can actually get to many other different covers as agroforest or open woodlands or whatever we can think about by combining these probabilities. But what I want to do in 2 examples following here is looking at how we can use this new data, how we can use the probabilities and the incredible time resolution from Dynamic World. And we'd like to play the video, please. So here I take you to the Okavango Delta in Botswana. It's one of those unique deltas. A delta usually ends up in the sea, not this delta. It ends up in the desert. So the rivers from Angola draw on in Namibia, go into Botswana, and end up in the desert. So when it rains, this becomes a wetland. When the rain dries up, it becomes a desert again. And this is so you can imagine how unique that system is and how much change there is in that system. So here you see on the left side, a sentinel image for every month averaged. And so you see how much dynamic issues there are in this issue. You see the forest, you see it getting more clouds, there's more rain, it gets greener, and then the rain stops and the whole area gets more drier. The desert comes back, and this is a recycle every year. And now here you see what comes with dynamic world. Dynamic world is able to see those time dynamics. Actually, inside the year, every month, a data set is produced, and you see here how well dynamic world picks up that change. And you see forests, you see flooded vegetation coming in, and then you see scrub and grasslands coming back in when it dries out. So that time sequence, that time resolution is very important next to the probability that we have. And what can we do with it? And I zoom in for a pixel. I made it a bit bigger, but it's actually just one pixel, where you look at the probability over time. And so what you see here in June, which is reasonable dry, you see that this pixel, the best probability is it is a forest. But then it's getting wetter in July and August, and actually it's now the biggest probability is flooded vegetation. So this is not a land use change, this is just a phenology change. Like here we leave, the trees leave, leaves. And so here we see the phenology change that's happening here, because we can have so many details inside the year on dynamic world. Now, what else we can do with here, we can actually add up all the flooded pixels and get an idea of how much area of flooded vegetation is there in every year. Now, other land use maps would have easily picked up the 2019 drought. Now, clearly lesser area of flooded vegetation. But what dynamic world can do is something more interesting with this much higher time resolution. You see that every year has a different signature. You see 2018, a very big spike, very high, much flooded vegetation, but very quickly came back to a desert condition. Well, if you see the first 2 years, you see actually much broader area, so less area flooded, but it took longer to stay flooded for a lot of the area. So you can imagine what kind of impact it has on this system. And so with dynamic world, we have an idea now that how we can see a better dynamic of the system and how different years would have different impacts on this very unique ecosystem. My second example is a bit closer to home. This is the state of Iowa. On the lower left is the Raccoon River. And again, we put a dynamic world picture over it. This is not specifically made for this area, it's just a general dynamic world data. But you see it fits quite well where there's forest, there are farmsteads. But again, I want to draw your attention to looking at one of those croplands, and you see the signature over time, the probability of this croplands. And you see here something, again, interesting what dynamic world can do with probabilities and this high time resolution. You see here the signature, the probability, and you see here that there are two crops, a main crop. It takes almost 4 months, and then you see a second crop, likely a cover crops. So other land uses would, in a yearly average, just say this croplands, but actually, because of the high sequence, we can see 2 crops. And that's get very interesting, so you can distinguish from different fields if they have 1 crop or 2 crops, which here in the US becomes even more important with this new act, which is going to Congress on having more climate action and growing climate solution, but it's actually about getting more cover crops. Those cover crops are good for sequestration, it's good fertilizing the soil. And so with this data, we might be able to have a better look at it. So those 2 examples, what I just showed, give you a better, because of the high temporal resolution, together with the probability, we can get new insights that were very difficult to get on our previous land use map before. On the 3rd example, I turn back.
So this is another awesome example. I love this example. So there's still uncertainties in the predictions for dynamic world for some classes, for a lot of classes. But if there's patterns of interest and a visible signal there, you can bring in your own training data to refine these dynamic world probabilities in a secondary classification. And this is an example done by Ollie Guinan on our team, who's got expertise in Irish peat bogs. And here's what a traditional peat bog looks like. when you have a farm many farms in Ireland have a dedicated strip of peat bog that's allocated to them, and they periodically cut away at the peat bog to heat their homes. And then here's what a industrial peat bog looks like. So they're mined in a really different pattern that emerges as a recognizable signal. And these industrial bog mines produce these briquettes that you buy in the store in Ireland. So Ollie, having practical on-the-ground experience of the local conditions, he created a relatively small, 70 labels per class training data set, dropping points around and building that label set of traditional versus industrial peat. And with this, farmland and trees to really, isolate, clearly distinguish those classes and those signals. And here's off the shelf how Dynamic World classified the region or built the region. So it kind of struggled with it, right? Like there's no class that's really confident in a single label, and it just so happens here that the top one label is yellow scrub and shrub with a little bit of uncertain sort of bare ground in there and some trees. But when you stop and think about a peat bog and you have those 9 classes in your taxonomy, what would you call a peat bog? It's kind of a mixture, like the real world. It's a bit of a mixture of these classes, a combination. So he used Dynamic World as a feature vector and trained a random forest classifier with his ground truth data. And the result is a derivative peat bog map showing areas of traditional and industrial peat bog mining. And traditional is this mushy pea color. The legend's a little small, but this traditional is this mushy pea color, and industrial is darker brown. So this was an experiment, right? This was done very relatively quickly. More work is needed to make something that's publishable or anything, and we noted that this doesn't really generalize to other peat areas in other parts of the world. But it does show the potential that using Dynamic World as an input combined with local knowledge, on the ground conditions, offers a great starting point for deeper analysis. And this is the entire, the map of all of Ireland classified as with peat. So I've got another example using JRC's Lucas dataset that's also in the Earth Engine data catalog. Xander Venter, who's here today and taught some of the sessions, mapped the class definitions of the Lucas ground samples to Dynamic World probabilities. And they're slightly, we're going to look at, I think, Dynamic World here just off the shelf. And then when he refined it, there's slightly different class definitions. So this experiment shows the details within the classes, sort of a rasterized version or a refined version of the Lucas data set. There's another example in also using JRC's data set done by Brookie Guster-Williams. And so we're looking at this region in Hungary. And he ran some experiments trying to identify grain throughout Europe. So here's straight up Dynamic World. Grain crops are these, in the Lucas definitions, are these wheat, barley, rye, and others in Lucas definitions. And you start to pull out a signal of those grain crops. And what we're looking at here is the results of the most confident models. Let's advance and zoom in a little bit. So each experiment used the same random forest classifier and the reference data. And yeah, we're looking at some of the outputs of the best model over Hungary. And this is zoomed in from that previous region. So this starts resolving the cereal crops, the wheat, barley, and rye are appearing in yellow. And again, this is sort of an example of how you can further derive insights from all of the probabilities. But is it good? Does it work, right? So we did some initial accuracy assessments for the different rows, which are summarized in this table. And the first row uses Sentinel-2, the cloud-free mosaics, all 10 to 20 meter bands. The next row uses just Dynamic World. And the third row is a combination of Sentinel-2 and Dynamic World. And I really want to draw your attention to the precision and the recall. Because there's about a 10-point increase in the precision and about a 20-point increase in the recall. Oops, can we go back a couple? Thank you. Back one more, back to that other one. And then one more. One more point. Thank you. And I guess the third point too is that you only have this like incremental gain in having a much better feature vector in combining the Sentinel-2 and dynamic world. And so the power of dynamic world to like pre-compute the land use features that you can use as predictors into another model. So again, these were all very kind of, off-the-cuff experiments. There's a lot more work needed, but the key result is that you can use dynamic world as analysis-ready data for land use. And in many cases, you'll see improvements over the same methodology of rather than just using Sentinel-2. So we're going to go work through this experiment, Brookie's experiment in part 2 in the workshops today at 11:30 in Discovery A. And now I'm going to turn it over to one of my favorite applications in the community, Jason and team at SkyTruth, who've been using dynamic world for change detection for their alerting platform. Oh, you've got one.
Thanks, Tanya and Fred. So like Tanya mentioned, I'm going to show how we're using dynamic world to enable users to monitor land cover change. So I'm the CTO of SkyTruth, which is a nonprofit organization that specializes in conservation technology. So our mission is really to build tools and data sets that enable conservation advocates anywhere to protect the environment, mostly using satellite imagery. We want the most eyes possible on environmental change, and one of the best ways to do that is with imagery from space. And something we've been thinking about for a long time is how to create a very simple change detection framework that can be applied to landscapes anywhere in the world, by anyone, not just people like us with geospatial backgrounds. And change detection generally is a hard problem for a couple of reasons, because context is important. So it's habitat specific. An algorithm that works in one landscape may not work very well in another. And it's also stakeholder specific. So a change that matters to one group of users might not matter as much to another. So when Dynamic World was released, we saw a really great opportunity to test and prototype some ideas we've had. And this is part of a project we're calling Verdant, whose goal is to enable simple, effective monitoring of landscapes around the world. And the reason we're thinking about this is to support 30 by 30. So hopefully, protected areas are going to be established very quickly all around the world to start protecting more biodiversity. And as they're established, they'll need to be monitored carefully to make sure they're providing effective protection. So that's the background. Now I'll transition to the demo. So the key idea of my talk is really captured in these 2 points on the screen. If you want extremely accurate change detection in a given landscape, you should probably train a model to do that specific thing. But if you want the ability to stand up quick, flexible monitoring almost anywhere in the world, Dynamic World's a really powerful tool to do that. It's similar to what Tanya was saying. We want to detect change with you, not for you. So the demo. First off, the interface that I'm showing up here is called SkyTruth Alerts. It's a completely free and open environmental monitoring and mapping platform we support. And it's also where we're experimenting with some of these dynamic world-based tools. And for the demo, I'll focus on southern Peru. This is a region where forests are being lost to illegal gold mining, and where for the past few years, SkyTruth's been working to monitor that mining in cooperation with local authorities. I also picked this area because we've actually trained a machine learning model in this region specifically to detect illegal gold mining. So this is a good testing ground to see how Dynamic World compares to a dedicated model. So first, I'll just pull up the Dynamic World data. You can see that this area is mostly forest, which you can see in green, with quite a bit of bare ground that's emerged, mostly due to illegal gold mining, which you can see highlighted in gray. So Dynamic World's doing a good job with the general land cover around the region, but how well does it do detecting changes to that land cover? And to answer that, we've tried to make a very simple process with just a few steps. So first, you define the before and after periods that you're comparing to each other. Then you define which land cover class you want to detect change in. And this could be every class at once, or it could be just a specific one. And in this case, we care about the emergence of cleared land where trees used to be, so I'll use the bear class, and we'll just leave everything else at default values. And then the last step is just to define how much the probabilities have to change before they're considered a change of interest to you. 25% seems to work pretty well in most areas, so we'll just leave that there. And if we run that, the results are actually pretty good. This all is calculated on the fly, so if we zoomed around, it would just populate the area around there too. And we've highlighted detected changes in the bear class in red, and we also automatically display before and after imagery from Planet Labs that's selected based on whatever time periods users choose, so it's easy to visually assess results very quickly. And again, this is all pretty flexible, so we could lower the probability threshold to be a little more inclusive and detect more potential change, or we could raise it to be more strict and only detect very large or persistent changes. But in this case, like I said, we'll stick with the default threshold of 25%, and we're actually doing a pretty good job. I'll show the comparison to the actual machine learning model in a minute, but so far so good. But, of course, we are getting some false positives, which you'd expect, particularly in riverbeds and riparian areas. So we needed a tool to help us filter out the changes we don't want from the changes we do want. And to help with this, we made a really simple pixel stats tool, which just pulls a time series of probabilities for each class for any point on the map that you select. So, for example, if I click on a true change region, you get a time series you'd expect with a persistently high probability of trees eventually being replaced with a persistently high probability of bare ground after the site gets cleared. And then if we clicked on some false positives, showing one of them up here, the time series shows that a lot of the pixels that are problematic are in the riverbed that flip between the water class and the bear class, probably because of changing water levels. So now that we know why the model's including these false positives and how they're different from true positives, the question becomes a little bit more refined. So now we want to know what combination of probabilities gives us the best land cover change model for this particular system. And we're still experimenting with the simplest ways for users to do that, but for now we added some simple class-based filters. And this particular filter I'm showing here just gets rid of classes where probabilities are very erratic over time, and in this case, we'll use that to filter out pixels where water is highly variable. And the model does get a little better. On the right, you can see the final results, and on the left, you can see the results of the machine learning model that we trained, and they're pretty similar. There's a lot of overlap. But no surprise, the model we trained pretty handily outperforms what you see there on the right that we created with Dynamic World. But of course it did. Any model that's trained to detect a specific change in a specific place are always going to be better than a very general, flexible system like we've used. But in this case, Dynamic World's a really effective starting point. That machine learning model took us months to develop, and what I just showed only took a few minutes, probably about 15 to 20 minutes when we initially sat down and did it. So in this case, in this particular system, a user could actually use what we created with Dynamic World to monitor change, and it'd do a pretty good job. They'd definitely get some false positives in the mix, but that's why we provide that before and after imagery. So every possible change that gets flagged can be verified visually. And just to run through a couple more examples quickly, we could do the same exercise over the Permian Basin in Texas, showing the expansion of fracking well pads over time. Or here's a burn scar in Greece, which you can see in the slightly transparent red in the center of the image. And once again, basically default values, it's doing a good job. And of course, there are a lot of cases where this doesn't work, but going back to the theme at the start of my talk, there's still just a lot of power in a tool that enables almost anyone, anywhere to quickly start monitoring a landscape they care about, tune it to their preferences, get automated alerts, and then verify those changes with high-resolution imagery, really anywhere in the world, and to be able to do that continuously in real time. And the other thing to say is that I think Dynamic World's really just the beginning. It's a really powerful demonstration of how many applications can be unlocked by data like this. There's just a huge opportunity for other real-time global data products like biodiversity indicators, biomass, ecosystem degradation, and plenty of others that would enable all kinds of really cool new environmental monitoring applications. And I know a lot of people here and on stage are already working on those. So just a couple quick calls to action before I turn it back over to Tanya and Fred. Everything I've shown is free and open to the public, so please check it out and send us your feedback. Again, this is a pre-alpha prototype. We've only been working on it for about a month altogether, so it's totally possible that if everyone here tries it, you'll bring it down to its knees, but that'll be a fun test for us. And the second one is, if anything I've shown relates to something you're working on, please get in touch with us. Like I said, we're a conservation technology provider, and we love to partner and support and elevate the good work that other people are doing, so let's talk. Thank you.
Oh, it's you.
So we're wrapping up. We just want to say, there are some paper published on this, and there's just a new paper coming out to compare the different. I mean, maybe you've seen that there are several new global data sets coming out. Xander here, came out with a nice publication about these different issues on comparing those different maps, and we are also doing that. And you see, there's a lot of accuracies, changing, and this is the global map again. So this is again for the dynamic world. I said we really think the power is also in the local maps, but here's accuracies compared to the global maps. And so you see that here in this publication, where I go it over to you, Tanya, again for the last few slides.
Yeah, this is
so bear with us.
So, we wanted to, emphasize this one other important point, and through the course of development of Dynamic World, we had concern over potential risk of, what if bad actors get a hold of the data set and use it to exploit the environment, or, local communities by targeting particular areas for deforestation or land seizure or more resource extraction or other, destructive acts. So, Google, together with the WRI team and others, worked with the Google AI Principles team to discuss a strategy to minimize the potential misuse. And we designed several safeguards for the data set, specifically considering human rights and surveillance issues. And we learned a lot in this process. And it's an iterative approach that we need to be, vigilant in the remote sensing community about potential misuse. So what's next for Dynamic World? Well, first, this is it's the first data set of its type, right? And we really want to hear from you. We want to know how quickly it gets you to actionable results. As I said before, we're committed to making it into the future. A lot of that also depends upon how we hear it benefiting the community. So that comes back as, we do really want to hear from you. So what's next for Dynamic World? We use the state-of-the-art cloud and cloud shadow masking process described in the paper. And still, errors in commission are often caused by cloud and cloud shadows. So when we find clouds and shadows, we throw out more useful pixels than we need to, and we're investigating how to include more of those useful pixels for analysis. We're also extending this work and forming new partnerships to drive new geospatial data, this new geospatial data ecosystem for commodity crops to help companies meet their net zero deforestation targets, as well as accelerate restoration. So talk to Fred and I if you have specific research ideas in around forests or around commodity-driven deforestation.
Well, this is clear. This is not a great big show. We want to make sure, Dynamic Worlds is the mix where with your input, you make your data set for your objectives, for your needs. And so we hope that dynamic world is so making you easier, making your cake that you want. And so I'm not a good baker, but Tanya is.
So Dynamic World at Geo for Good, we're having a couple training workshops today. I want to encourage you to attend those and roll up your sleeves and get your feet wet in these training sessions. They'll be hands-on. We'll be joined by our developer relations team, Tyler Erickson, the engineers who worked on Dynamic World, our partners at WRI, and the author of the community tutorials, Ujjwal Gandhi. So bring your research ideas and explore the data. And a huge thank you to Jason, Fred, and Jason and the rest of your SkyTruth team, Fred, WRI, National Geographic Society, who built the training data set that we used for Dynamic World. Huge thanks to the engineering team of Dynamic World. A special shout out to Chris Brown and Oliver Guinan, Valerie Pascarella, Wanda Cherwinski, Simon Ilyushchenko, a lot of people behind it, Kurt Schwer, who did a lot of the cloud masking. So we'll see you in the breakouts, and back to Karen and Michael.